Is that audio? Audio? Oh, you're gonna mix me up, I see. Is that my soundtrack? That's my theme music. Okie doke, let's see how this works. SQLAlchemy Session. So who is familiar with SQLAlchemy, ORM? Okay, so good. So I think this talk is probably more meaningful to people that have used SQLAlchemy. You know, like a lot of my talks, it kind of walks the line between what do other ORMs do and what does SQLAlchemy do and why is that possibly better. So we're talking about the session here, which is the thing you put your objects into and it does all the work with your database. And the talk here is going to focus on how the session is organized in terms of the database transaction. So we'll do a little review of a database transaction, and we're all pretty familiar with like the ACID model and stuff like that. Transaction, here's my quick 4 bullets on that, 4 bullets. Primary system employed by relational databases for managing your data. It's a pretty generic statement there. It kind of provides a scope around a bunch of operations with things that we like, and I'll go through those things in a second. And then the transaction follows this model called the ACID model, which is, as a lot of you probably know, is an acronym. So we'll do all 4 letters of the acronym just to review, because actually SQLAlchemy Session interacts with at least 3 of those letters in a specific way. Oh, one more. Relational databases usually use transactions for all operations. Like if you go to your Postgres shell or something and you begin entering statements, you'll see that those statements will auto-commit, but the database engine is still using a transaction behind the scenes. It's just you don't see them because they're auto-committing. So there's always transactions in play in most cases. They just often are auto-commit. So the ACID model. The A in ACID stands for atomic. And atomic means that you can do a bunch of things in a transaction that don't actually affect the final state of the database until you commit them. And if you roll back the transaction, then everything you do is gone. So in this little picture I have here, there's kind of the green box is a table that stores, in this example, email addresses. And the green bars are little rows being added to the table within a transaction, but then the transaction is rolled back. So the state of the database is at the bottom. It begins with a table with 1 row and ends with a table with only 1 row because the stuff in the middle was rolled back. So that's the ACID model. It's atomic. You can roll back multiple things at once. That's the A. Easy, right? Okay. The C is consistency. Relational databases like to use what we call constraints. They like to validate data that's coming in that it meets a lot of criteria. And some of those criteria include that you have fields that are not nullable. They have to be present. You have a primary key, which has to be unique in terms of that table. You have what's called a foreign key constraint. Water. So I'm going to dry out. A foreign key constraint is when you have 2 tables where one table refers to rows in the other table. You'll have a column or columns in the dependent table that refers to the primary key identifiers in another table. Sometimes the same table, but usually 2 different tables. So in this case, if you want to insert a row into a table called addresses that has a foreign key to a table called user, the database won't let you do that unless the user ID column you're giving it, in this case, is referring to the primary key ID of the user table. So that's a good thing. It keeps our database in a state known as consistent, relationally consistent. But what these constraints, the effect they have is that you can't just put data in a database piecemeal. You have to have the data kind of prepared in a certain fashion. You have to have a row that has all the not nullable fields present before you can add the row. And if your row has foreign key constraints, the parent row has to be present first. There are some exceptions to that, like deferrable constraints, but that's not a generally used feature right now. Most databases don't really support deferrable constraints, but different topic. Anyway, you normally want to put rows in a certain order. So the SQLAlchemy session is going to have to take steps to work with that. The I in ACID is for isolation, which I'm going to do this in a slightly hand-wavy fashion, because isolation is actually a big topic. It's complicated. It kind of means that things that happen in the transaction are not visible to the outside world until the transaction is complete. And to a greater or lesser degree, it also means that things that happen in other transactions on the outside, you might not see those changes apparent in your transaction until your transaction is over. There's such as repeatable reads refers to if you load a row in your transaction and then outside someone commits some change to that row, you might see the old version of the row in your transaction if you have a higher degree of isolation. So isolation historically was achieved using locks of table and row locks. So you would have things would have to wait for things to happen. So in this picture I'm trying to illustrate, there's a second transaction there that can't read the address table until the first transaction is complete. So that's the locking style. But most modern databases today use a system called multi-version concurrency control, which means that each transaction gets a transaction ID or a timestamp. That transaction ID is applied to copies of rows that are local to that transaction, and then when the transaction commits, that version of the row becomes the official version. So different transactions can run concurrently, looking at copies of the same row with different versions of data with a different transaction ID. So what MVCC gives you is just a relatively higher degree of isolation with a relatively lower level of locking. There's still some locking happening. It's a whole topic for people much more intelligent than I am, but I just have in my brain the sense that your transaction is kind of, to some degree, kind of isolated from things happening. And that's as far as my brain goes with it. And then finally, the D will be an easy one. We'll have Borat explain durability. Basically, durability generally means after you commit the transaction, the database says the commit succeeded, you can be pretty sure that the data is safe on disk. And I actually went to Wikipedia to see if there's some more involved discussion. It didn't seem to have much. So durability is probably a big deal, but we don't think about it too much with relational databases. It just kind of happens. So that's kind of my view of a transaction. And so how do we build object relational mappers to interact with transactions in an effective way? And then, as a lot of my talks go, we'll start with what I call our first ORM, which means we're going to deal with an ORM that, SQLAlchemy wasn't the first ORM I wrote. I did all kinds of database, interaction layers at all my different jobs I've had, and I've done database layers like crazy, and a lot of other people have too. There's a lot of other ORMs, and there's a kind of a way we all go and do it at first, and it kind of follows a model called active record. This is kind of a quick configuration of this ORM. It's really not that important. Like SQLAlchemy's configuration is not very different from this, but let's just suppose we have two tables, and I'm going to keep this user and address table, I'm going to try to keep it consistent all the way so that by the time we get to the end, you'll know these two tables really well, and you'll know what I'm talking about when I refer to the foreign key. The user table has an integer primary key, a surrogate integer primary key, and it has a string that holds like a name of a person. And then the address table has a string column called email, which has an email address, and also a surrogate primary key integer column, and a foreign key to the user table. So when you have user to addresses, that's called a one-to-many relationship. So the user table has got its primary key, and then many address entities can refer to the user entity. So far, this should be people should understand this kind of thing. It should be pretty cut and dry. It's the same, if you read the SQLAlchemy tutorial, it's the same exact model we have there. It's all over the place. Okay, so no big deal. And as far as the syntax, it's not SQLAlchemy syntax. It's not that important. The point is, when we have objects like user and address objects, the persistent side of this, in my view, active record means that the object that you've declared as a mapping to a table is also the persistence interface to the database. Meaning, if you want to talk to your database, you first figure out which table you want to deal with, like the user table. Then you deal with the user object, and then you're going to use commands on a user object to emit commands to the database, like an insert or an update. So say here we make a new user object with name of Ed Jones, and then we say user1.save. Can people see the code there also? Because it can't see the code. It's going to suck because there's a lot of code. Well, you can see this. You can see there's 4 lines, right? There's 6 lines and 7 lines. So the first line, wow, you guys can't see it. That sucks. The first line here is basically we're making a user object, and we say user1.save, which emits an insert statement immediately. And then we have we change the name, and then say .save emits an update statement. So it's just like save, insert, and then if we do a delete of an object here, you get a delete statement. So it's kind of like one-to-one. As soon as you tell the object to save, it corresponds to one, what we call a DML statement, data modification language. So even though you can't see the code, you kind of know what I'm saying, right? All right. All right. So anyway, let's suppose in this blurry thing you can't see. There's some operations with a user object in the middle. If we want to have a transaction, like say we want to do several operations at once and have them in this atomic unit that we like so much, our first ORM has a global variable called transaction. And this is a pattern that I've seen a lot. I used to do it. SQLAlchemy still has some dark corners that can do this kind of thing for you, but we don't recommend it. You can make basically this global transaction that says transaction.begin, and then you work with your user and address objects. You do save and delete, and it'll emit all these insert update statements. And then you say transaction.commit, and that'll commit the transaction. It's a reasonable system. There's no explicit linkage between the transaction and the objects we work with. There's basically a thread local. Do people know what a thread local variable is? Basically, it's like having a global variable, except other threads won't get in the way with your global variable. So it's a way of sharing state between two different systems without passing variables along to call. So basically, the transaction is global. The user object, when it says .save, will consult this global transaction, and then it kind of works. So that's kind of the first ORM's approach to transaction demarcation. So also with this system, because the user class and the address class are kind of by themselves, there's no coordination between different instances of objects that are loaded from the database. The system by default works in auto-commit. There is no transaction by default. So really when you say, user get ID number 5, you get a user object with primary key number 5, and then someone else gets user primary key number 5. There's no relationship between those two operations. They're not necessarily part of the same transaction. The two operations will return a different instance of the user object with the same data from the database, but they're independent. So if you modify the state of one of the objects, you won't see that in the other object because the other object has no relation to you at all. And vice versa. So then what happens is you can actually modify state in memory that doesn't match the database, but then also doesn't match itself in memory. It's not consistent. Now, we'll go, I feel that there's some problems with this, which I'll lay out in, I think, the next slide. All right, so let's wrap up active record persistence. Someone else writes these talks for me, I just read them. So now, okay, active record persistence, just to wrap it up. So now you can see these letters, I'm hoping. Okay. The means of persistence is provided by the interface of each individual mapped object, like object.save, object.delete. Objects aren't coordinated on a particular transaction by default. It's auto-commit is the default. The objects don't have any connection. There's no reconciliation of identity. They're basically islands onto themselves. And persist operations are immediate. So if you say save or delete, you'll get an insert update or delete immediately. So the issues with active record, now all of these issues, the examples here, which you probably can't read, are a little bit contrived, and none of them are things that you can't overcome in active record, but they're things that I think we can do better than. So for example, this example is showing two different functions that deal with a user object. One of them loads a user with primary key number 5 and changes some field on the object, and then the other function loads that same row from the database and then makes a decision based on the change that the first function created. So there's the dependency between these two functions. You need to call the second one second, and you need to call user process 1 first, and then the other one second, so that the state that you expect happens. But because both of these functions are hitting the database to get the row back, that's not all we need. These also need to coordinate on the database, because when user process 2 runs, he's not going to know the change that user process 1 created unless user process 1 also emits an insert statement. So what we're saying here is that if two different functions want to query the database and pull up some state, if one of the functions is changing the state of objects, that function has to make sure he pushes the changes out to the database first before the second function can get that information. So it kind of adds this dependency that we may have to make sure that if you're doing two separate queries, you have to coordinate on the database at all times because there's no other coordination between these two objects. And this is not something that we can't work around. And if we know it that we didn't save this object, so we have to make sure we save it first before we go to the next function. It's not a big deal, but there are ways to make it so that we could coordinate in memory and not have to worry about that happening. So this is kind of an issue with active record, in my view. Another issue with active record is that because we're emitting these insert, update, delete statements immediately, remember I talked about consistency. There's kind of rules in the database's point of view as to when we can emit statements and in what order. When we have to emit those statements manually, we have to make sure that we push the statements out in the order that the database expects. So this code, which is probably a big blur to you, because I had a lot of code in my slides for this one. We're reading a data file that has information about users and addresses, and then we're kind of copying that data into user and address entities and persisting them. When we write the code, if we're getting the data in not the same order as what the database expects, we have to make a lot of decisions in our code as to when we push the statement out for the address, when we push the statement out for the user. We have to make sure that all the user rows are inserted because the order in which statements get sent to the database is actually something that we can predict. It's not like we have to guess. So basically, when active record means that we have to push out insert update statements immediately, we have no way. Well, we have to manually figure out which statements go where. So this slide is trying to show that it just complicates our code, adds more work that we have to do that maybe we wouldn't want to do. Active record, because when we load rows from the database, we don't necessarily have any transaction in play. It's auto commit. There's no real easy way to figure out when an object is stale. If you have an object here, like the first blur up there says that we're loading user ID number 5 and changing his name to a new phrase and emitting an insert statement. And then the second part of the code here is loading that same row from the database and changing the value to something else. After that, we go back to the first user and ask him, what does your name field say? He's probably going to give you the name that he had in memory, not the one that was in the database, because there's no automatic, that helps, there's no automatic way for the user object to know when he needs to go back out to the database. We could maybe say, hey, ORM, can you please refresh user one's name field? And he'll do that, but we have to do that. We have to decide to do that manually, or we have to make the ORM such that the name field is always auto-refreshing every time we hit it, which would be very wasteful. And the problem here is that because the active record system doesn't require any kind of transaction, any kind of unit that ties together a series of operations, there's no clean demarcation where we know to expire the data we've worked with and that we need to go back to the database and get new data. And then later on, user 2 changes his value again, the transaction's rolled back, but then user 2 still doesn't have the correct state because he doesn't know to expire his state. Basically, there's no auto expiration going on, and there's not a good place to do it. And then this is the final, most dense example, which I really tried to make this code shorter. So if you look at, I'll put the slides in the blog, and you can read the slides more carefully. What this is trying to illustrate is, we have some lighting. It's fun. The lack of behavioral constraints creates confusion. And what this code is trying to illustrate, if you could only see it, is that this code is basically broken. There's two different functions here, and like we would say that they run in two different threads or processes. Does everyone know what the producer-consumer model is? The general idea of producing something, putting on a queue? I see some heads nodding. So this is one thread here is a producer. He has a long-running transaction. He's loading rows from the database into user objects, putting those user objects onto a queue, and then a user-consumer thread is then popping user objects off the queue and then doing something with them. In this code, though, the code is broken because the producer is occasionally inserting the user row fresh into that transaction and then putting it on the queue. So the consumer will then pop that user off, and then if he tries to do something with that row that's not compatible, if he tries to, like, say, in this example, delete that row, that operation will actually silently or explicitly fail because the producer has inserted a row, but he's in a transaction, which, remember, the I in ACID is isolated. That row can't be seen by the outside world yet until the transaction is over. So the consumer will do a delete, and the delete will either it will not match any rows, and the ORM will either just silently fail to delete the row, or it will complain if the ORM is designed such that it checks for the number of rows matched. But the point of this code is just that it will fail based on the data. So if the user data happens to be all clean and we don't insert any new user rows, the code will succeed. We won't know anything's wrong with it. Even though the code's been written incorrectly, we're not going to know unless the data just happens to have a user that was inserted at the top and is being deleted at the bottom. Both are two things that might not happen. And that's because the active record ORM here is really not trying to help us at all by saying, hey, this user object is actually from a different transaction. And you're not really telling us that, so it has no way to know. So this is a problem a more intricate issue with active record. So, given those issues, and I'm hoping at least some people can see that they're somewhat issues if you fit them yourselves, the session solves all of those issues. All right. Great, I got a laugh. Great. You didn't laugh at Borat, but I got this one. All right, so, so the session strategy is, what is it start? So first of all, we're going to say goodbye to auto-commit. Explicit transaction is always present. So I'm hoping, I'll show you this some more, but from those examples, maybe you could see that the fact that there wasn't a transaction necessarily present was kind of hurting us. It wasn't giving the tool a clean way of knowing how it should be coordinating things. The session maintains a set of transaction state in a cache, and this state consists of rows. The rows are rows that we know to be present in that transaction. A row is typically only present in the session if it was selected from a select statement or inserted in the span of that transaction, meaning that every row that we deal with as a row, we know that the database transaction knows about it. We don't accept rows from, with exceptions, we generally don't accept rows from the outside world because we're dealing with this transaction here. We know nothing else about anything else because we're assuming that we're isolated. So when an object, like your user or your address object, is associated with a session, they're not like these freestanding dictionaries of stuff. They are, but meaningfully, they're actually proxies for rows in the span of that transaction. And that's really the only meaning that they have to us. And if there is no transaction, those objects are essentially dead to us until they associate themselves with another row in another transaction. And they're also represented uniquely on primary key identity. So if you have a user ID number 5, there's only one of those present for that session. And then changes to these objects, if we have user address objects and we make changes to that dictionary, those are pending changes. We're going to push them back out to that same transaction using a pattern called unit of work, which is going to handle the details of. So some pictures, now you can see a little better. The object as row proxy. An object is said to be persistent when it acts as a proxy to a row present in the transaction. And this row is normally always known as the result of a select or an insert. So in this diagram style, the dotted line box in the middle is the transaction. So I put a copy of the address table in there because the multi-version concurrency control really makes it as though there's like a copy of the address rows that we care about in that middle zone. So the red box is the SQLAlchemy session. It only deals with the transaction box in the middle. It never really talks directly to the database's physical storage. We're always seeing the world through one transaction at a time. When there's no transaction present, we've committed or rolled back, that box goes away. The green address objects in our session on the left side are basically expired. We know they're still objects that represent what was once a row in a transaction, but now they're expired. We take all their dictionary contents and clear it out. When you hit any attributes on those objects again, the session will be like, okay, let's go talk to the database again. Let's open a new transaction, get the row back again, so now we're back online with a new transaction. So we only look at data in terms of an ongoing transaction and never in any other way. An object that's outside the session, like a brand new object we're going to put in the database, is called, doesn't correspond to a row yet, does not correspond to a row yet, is said to be transient. And an object inside of the session, but not yet corresponding to a row, the flush hasn't happened yet, is said to be pending. Another state that we won't talk about too much here is called detachment. If you have an object that represents a row, but it's been pushed out of a session, it's said to be detached. It's useful for caching, but not much else. And then the unit of work pattern, this is kind of my excuse to use a lot of colors. The unit of work pattern lazily flushes only those rows and columns that have changed, ordering its operations in order to maintain consistency. So I shouldn't spend too much time on this slide because I'm going too slow. The red box, the session has some objects, users and addresses that are in the dirty list, like changes to be flushed, brand new objects to be flushed. The unit of work organizes the work to be done in terms of buckets, and then it sorts the buckets in terms of which tables need to be affected first, which ones second, and then it pushes the rows out to the transaction. So we're just moving from left to right. Data's moving from left to right, pushes the rows out to the transaction in the correct order, and then when the transaction commits, the data will be pushed to the database. And if I get all the way through the end of this talk, you'll see an animation showing some of this at work. So hopefully that'll be fun if we get there. Okay, so where did the session come from? How did I know how to do this? I read a book. I read a book called Martin Fowler's Patterns of Enterprise Architecture. It's a great book. Originally, we looked a lot at Hibernate for Java, which has an object called the session, which is actually similar to the SQLAlchemy session. The Hibernate session is also adapted into a specification called JSR 220, which a lot of very intelligent people spent a long time really thinking how this session model should work. And then also SQLAlchemy itself, our original session model was a little bit loosey-goosey. We learned a good lesson on how to make it much more strict and correct by looking at the Storm ORM for Python. So Storm ORM is not a very widely used ORM. It's very simple. It doesn't do nearly as much as SQLAlchemy does, but they have a very good transactional model, and that's, I credit Storm for showing me, okay, that's how to do it. Great, so credit them. So watching the session solve all of those issues. So we'll go through all the same blurry code you couldn't see before in terms of the SQLAlchemy session. Objects are stored in an identity map. So if we have two different functions calling up user ID number 5, we get the same user object back each time from that session. And the key here is that these two functions, unlike the previous ones, are accepting an argument, which is the session. So instead of having to pass objects around to different functions who need to coordinate on some object, we pass the session around between different functions, and that means that we're actually coordinating on the operation, not just objects. So the session really represents the operation in progress, and it's like a context, and it makes it easy to just do whatever we need to do, and it's all in terms of this one session, which then coordinates all the identities. So we don't have to worry about rows not being flushed out to the database yet in most cases. We can deal with them in memory. The unit of work will transparently flush them out as we need. So we have basically less things to worry. We have to worry about the session. That's this new thing. Oh, a session, where do I do it? Where do I make one? But once we get over that, there's all this other work that we don't have to do anymore because the session is coordinating our activities. The unit of work pattern aggregates changes and emits as needed. So in our data file example, we just add objects to the session as we get them. We don't worry about, in most cases, about when they get inserted. It doesn't matter. The unit of work will basically flush every time right before we do a query. It'll flush what we have pending. So it doesn't remove the need to sometimes worry about the order of things, but it makes the process much easier. We just occasionally have to maybe flush out to the database, or we can just let this unit of work totally be automated and just say commit, and everything will be flushed for us. We don't have to deal too much with the ordering of statements. The unit of work will do that for us. It becomes a much more coarse-grained activity, less things for us to worry about. Data is expired when transactions are ended, so there's no stale data. And so because we're making you decide when your transaction ends, like we're making you decide where your session is, who's coordinating on that session, and when is it going to be committed or rolled back. You, the programmer, have to do that job. You give SQLAlchemy a lot of good information as to when it should be expiring the data. So in this case, if we have two different sessions, both dealing with the same row in the database in two different transactions, the first session makes a change, the second session makes a change. We go back to the user object from the first session, and he says, well, my transaction was committed, so I know that I've been expired. I've got to go back and say, okay, go get a new transaction and get the fresh data. So in this example, you can hit the user 1 or user 2 objects all you want, commit, roll back, whatever you want. They will always show the data that's in the database. You'll always get with it. You will never get any kind of memory data that's not really there. It's always fresh, assuming a high level of isolation in your transactions. If you have like dirty reads, then you'll have problems. But we're assuming that you've worked things out so that your isolation level is high enough to meet the kinds of concurrency that you're dealing with. So objects that are, and then finally, this is the more strict usage patterns. In our example of the producer-consumer, when we try to take a user object from one long-running transaction, put him on a queue, and have the second transaction read him back, if we take the user object from the first transaction, the second function will reject it out of hand. He'll be like, hey, this user object is not from my transaction. He does not proxy a row that I know about. So he will reject it out of hand, and this code will fail always. It won't just break when the data is a certain shape. It's going to break in all cases because we're doing something bad. And because the session is there, and because we have explicit transactions, the ORM can make better decisions as to, hey, you're doing something that you shouldn't be doing. So more rigid structures here means that we have less chance of doing things incorrectly. Does that make sense to any? Yeah? All right. So I'll just note that Zed Shaw thinks this is totally wrong. He basically thinks I'm stupid because he doesn't like that. So part of my motivation here was to show this is why it works that way. Okay, so and then we're at the live session demo. Okay, so what I did here, because I wanted to just show graphically, because I've been dealing with this session thing for like 7 years now, I see it in my head. So I wanted to try to do something that could show you what it looks like in my head. So it's going to be a graphical thing. We're going to do this SQLAlchemy model, which is the same model we've just been dealing with, the user object, the address object, the same fields. We're going to flip the many to one to the user has a collection of addresses on it in this case. So user.addresses is a collection of addresses. And then the code that we're going to animate, and the way I did this was I basically used SQLAlchemy events. So as this code would run, I used events and also some other Python hooks to track when different state changes occurred. And then those state changes, I would emit commands to a big JavaScript file. And then the JavaScript file is going to actually cause this HTML5 screen to change state based on commands. So basically, I ran this code into a special event catcher that turns it into a set of animation sequences. So we create a new user. We access the addresses collection on the user, which makes a new collection. We add to that collection 3 address objects. We create a new session. We then add the user object to that session, and then in SQLAlchemy, that add operation will cascade to the 3 addresses attached to the user. We commit the transaction, which will flush all those changes out. The user is then expired. We'll then access the addresses collection on the user again, which will hit the database, start a new transaction. We're going to look at the first address in that collection, change the email to something, and then we're going to commit the transaction again. So let's see if we can do this part. You see it? Great. All right. So I'm going to get my mouse. The mouse is over here. So what you see, the big cylinders in your database, and those 2 boxes are the user and address table. And that's the SQLAlchemy engine down there, and there's a connection pool, and there's 3 connections, say open, so there's no data in the database yet. And the first thing we're going to do is get focus on the window. The second thing we're going to do is make a new user object. Oh, I pressed the wrong button. Let's do this. Reset. So that's the user object. So it's the yellow box, and I'll put this on my blog, so you can actually zoom into it if you want to zoom and do that. So just to see more, it's a little glitchy because I'm not an HTML5 expert, but it's kind of works. So we make a new user object. We set the name attribute to the value ed, so its username is ed, and then we say user.addresses. It makes an empty collection, and then we add an address object. We create a new address, 1, set the email field, 2 addresses, set the email field, 3 addresses, set the email field, and then we're going to start putting those addresses in the user addresses collection. So this is really one step at a time. This is like the atomic level of code. So there's the address being appended, 2 appends, 3 appends, great. Now we're ready to put this whole thing in the session. There's the session. So the little boxes inside are like various elements of the session that are public. There's the new collection, which is objects that are pending. The dirty list is objects that have pending changes to be updated. The deleted list, objects to be deleted. The bigger box is the identity map. Those are persistent row proxies, but like every object that proxies a row will be in the identity map. The transaction represents all the connections that we know about pointing to databases. And then the next is we're going to start adding the user to the session, so the little yellow reference goes up in the top there. That operation cascades to the 1, 2, 3 address objects associated with the user. Now the flush begins. So we establish a connection. You can see it popped into the transaction box there. The database creates a transaction ID where it's going to store all the version of changes that we're going to create that are pending. And then we insert the user row. The database creates a new primary key for that row and sends us back the primary key. We then have to take that primary key and populate it into the foreign key column of all 3 address objects. So then what it does is it sets user 1's identity to value 1, and then it populates that number 1 into the user ID foreign key of the address objects, which is actually, you can't see it, but it's actually happening in those little address boxes if you were to zoom in. And then we insert the address rows. That's 1 row and 2 rows and 3 rows. So now the transaction's got the data as we want to see it. We then move the objects that are in the new collection to the persistent collection. They're now proxying to rows that are in the transaction. And then the flush ends. The snapshot is committed. The transaction goes away. The data we just had there moved to the right into the permanent storage. It's basically durable. So Borat at play. And then we expire all, there's no more transactions, so we're going to expire all the data on all the address and user objects. Because we expired the addresses collection on the user object, it so happens that the 3 address objects are going to be garbage collected by Python, using reference counting. and then the connection is removed, and then the transaction ends. The session, because it always is in a transaction, starts a new transaction, but hasn't actually talked to the database yet. We're now in the dormant state again. So now we're going to do the next operation, which is going to say user.addresses. Let's reconnect the database. Let's go get the transaction. Let's go get the user table back. Let's get his row back. And let's get the addresses collection. Select star from addresses where user ID equals 1, and we get those 3 address rows back into the span of our transaction. So again, these rows, we know about them in a transaction again. We create proxies for those rows. So there's address row 1, 2, 3. And then we want a user.addresses, so they go back into the user addresses collection. And they go 1, 2, 3. So now we're back to user.addresses. Then we modify the email state on address 2. And then that has the effect of the address 2 popping up into the dirty list there. That's a pending change to be flushed out. Flush begins, we do the update statement, the row changes, the flush ends, the snapshot is committed, and then we expire all the attributes again, and then the garbage collection occurs again, because user.addresses is not strongly referenced anymore, and connection turns off, and then the transaction ends, and a new transaction in case we do another operation, and then in this example, I think the user is garbage collected. And that's the end of it, and then if I just do start, you can kind of just see it happen, and it's kind of like watching like Christmas lights. Like we'll have like a Christmas tree with SQLAlchemy objects flashing on and off. So this is kind of originally I thought I would just run this thing and have people see it, but you wouldn't know what the hell it's doing. So I figured let's go through it first. So now you can appreciate the zen of the SQLAlchemy session, just running in this goofy graphical way. So as long as I see at least 2 people laughing, I know it wasn't a total loss. So this is just HTML5, so I can put this up, and if you want to play with it, it's kind of a funny thing. So we do questions? I'm assuming that microphone would be for questions.
Hey, so with the unit of work pattern, how do you maintain your sanity if you're reordering how statements flow?
So the question is how you maintain your sanity with unit of work if you're reordering your statements? Mm-hmm. Well, why would you need to reorder the statements beyond what the deterministic? Because basically the unit of work is going to basically look at the statements to be emitted. It's going to sort them for you into the order that the database expects. Okay. So it's built to work with the normal constraints of the database. So if you have a user and address rows, it will always make sure for the insert side, it'll insert the dependee row before the dependent row. And then on the delete side, if you're deleting all the addresses and users, it'll delete the addresses first and then delete the users. There's a lot more going on if you do updates and other things, but that's the simple version, is that it's going to make sure to as much a degree as possible to do the instructions in the correct order. Okay. That's the basic idea.
Okay. And is that pretty consistent across all databases? Or
all databases are all ultimately the same thing. They all have the same foreign key constraints going on, so it's all the same insert, update, delete statements. They all speak the same language. Okay. So it all works out.
Cool.
Yep.
Would it be able to extend that concept of session across multiple databases, like when you have shards?
Right. So when you look at so the question was, can the session concept extend to multiple databases, right? So if you go here, I'll go here because I'm the one with the mouse here. So you have this box, this transaction here, and then when you connect to the database, it puts one of these database connections in that box, and that's what we're talking to. If you had another database here, and then you started talking to another database, it would put another connection in the same box. So the session transaction is a collection of database connections, one connection per database backend. So what you can do with SQLAlchemys Session is you can orient it so that different classes go to different databases, which is called vertical partitioning. Mm-hmm. And there's a more sophisticated system that you can use to make different rows go to different databases called horizontal partitioning. So horizontal partitioning is hard to do because it's tedious to figure out which rows go where, but it can be done. Another approach, sometimes it's simpler just to use 2 different sessions, depending on how your app works out. But yeah, the session will very easily vertically partition.
Cool, thanks.
Yeah.
Hey, do you support different transaction isolation level?
Support different?
Like isolation level for transactions, such as read committed,
Right,
repeatable read.
okay.
And
Yeah, so the question is, do you support different isolation levels? So SQLAlchemy deals with the database through, get Hello Kitty back, deals with the database through a Python system called the Python Database API. And the Python Database API is the system that we use in Python to talk to relational databases. And the DB APIs usually have some kind of features or options to modify the isolation level. And sometimes in some database backends, we just emit a statement like set isolation level to be X, Y, or Z. So SQLAlchemy can change the isolation level, but the workings of the session are built around the assumption of a highly isolated environment. So if you have things like dirty reads or something like that, and you want to actually work with dirty data, you can, but you need to be explicit. You have to go in your session and say, hey, this user object is going to see some uncommitted data somewhere else, and I want to actually see that. You can expire that object so that it'll go back out to the database. So the session is automated in terms of a purely isolated transaction. And to the degree that your transaction is not isolated, if you set the isolation level lower and you want to work with current transactions that are not isolated, you can manually expire objects so that you see it. So there's a path. It's not as easy, but there is a path to that. Yeah.
thanks.
ID column you're giving it, in this case, is referring to the primary key ID of the user table. So that's a good thing. It keeps our database in a state known as consistent, relationally consistent. But what these constraints, the effect they have is that you can't just put data in the database piecemeal. You have to have the data kind of prepared in a certain fashion. You have to have a row that has all the not nullable fields present before you can add the row. And if your row has foreign key constraints, the parent row has to be present first. There are some exceptions to that, like deferrable constraints, but that's not a generally used feature right now. Most databases don't really support deferrable constraints, but different topic. Anyway, you normally want to put rows in a certain order. So the SQLAlchemy session is going to have to take steps to work with that. The I in ACID is for isolation, which I'm going to do this in a slightly hand-wavy fashion, because isolation is actually a big topic. It's complicated. It kind of means that things that happen in the transaction are not visible to the outside world until the transaction is complete. And to a greater or lesser degree, it also means that things that happen in other transactions on the outside, you might not see those changes apparent in your transaction until scope around a bunch of operations with things that we like, and I'll go through those things in a second. And then the transaction follows this model called the ACID model, which is, as a lot of you probably know, is an acronym. So we'll do all 4 letters of the acronym just to review, because actually SQLAlchemy Session interacts with at least 3 of those letters in a specific way. Oh, one more. Relational databases usually use transactions for all operations. Like if you go to your Postgres shell or something and you begin entering statements, you'll see that those statements will auto-commit, but the database engine is still using a transaction behind the scenes. It's just you don't see them because they're auto-committing. So there's always transactions in play in most cases. They just often are auto-commit. So the ACID model, the A in ACID stands for atomic. And atomic means that you can do a bunch of things in a transaction that don't actually affect the final state of the database until you commit them. And if you roll back the transaction, then everything you do is gone. So in this little picture I have here, there's kind of the green box is a table that stores, in this example, email addresses. And the green bars are little rows being added to the table within a transaction, but then the transaction is rolled back. So the state of the database is at the bottom. It begins with a table with 1 row and ends with a table with only 1 row because the stuff in the middle was rolled back. So that's the ACID model. It's atomic. You can roll back multiple things at once. That's the A. Easy, right? Okay. The C is consistency. Relational databases like to use what we call constraints. They like to validate data that's coming in that it meets a lot of criteria. And some of those criteria include that you have fields that are not nullable. They have to be present. You have a primary key, which has to be unique in terms of that table. You have what's called a foreign key constraint. Water. So I'm going to dry out. A foreign key constraint is when you have 2 tables where one table refers to rows in the other table. You'll have a column or columns in the dependent table that refers to the primary key identifiers in another table. Sometimes the same table, but usually 2 different tables. So in this case, if you want to insert a row into a table called addresses that has a foreign key to a table called user, the database won't let you do that unless the user of your transaction is over. There's such as repeatable reads refers to if you load a row in your transaction and then outside someone commits some change to that row, you might see the old version of the row in your transaction if you have a higher degree of isolation. So isolation historically was achieved using locks of table and row locks. So you would have, things would have to wait for things to happen. So in this picture I'm trying to illustrate, there's a second transaction there that can't read the address table until the first transaction is complete. So that's the locking style. But most modern databases today use a system called multi-version concurrency control, which means that each transaction gets a transaction ID or a timestamp. That transaction ID is applied to copies of rows that are local to that transaction, and then when the transaction commits, that version of the row becomes the official version. So different transactions can run concurrently, looking at copies of the same row with different versions of data with a different transaction ID. So what MVCC gives you is just a relatively higher degree of isolation with a relatively lower level of locking. There's still some locking happening. It's a whole topic for people much. Is that audio? Audio? Oh, you're going to mix me up, I see. Is that my soundtrack? That's my theme music. Okie doke, let's see how this works. SQLAlchemy Session. So who is familiar with SQLAlchemy, ORM? Okay, so good. So I think this talk is probably more meaningful to people that have used SQLAlchemy. You know, like a lot of my talks, it kind of walks the line between what do other ORMs do and what does SQLAlchemy do and why is that possibly better. So we're talking about the session here, which is the thing you put your objects into and it does all the work with your database. And the talk here is going to focus on how the session is organized in terms of the database transaction. So we'll do a little review of a database transaction, and we're all pretty familiar with like the ACID model and stuff like that. Transaction, here's my quick 3 bullets on that, 4 bullets. Primary system employed by relational databases for managing your data. It's a pretty generic statement there. It kind of provides a